Hey, what's up guys? Welcome back to another video. So, I want to briefly explain the history of this before I jump right into it. So, I've conjectured this idea about a year ago, and I've fallen out of interest of it for whatever reason, right? And I'm resurrecting my interest back into it with more experience in math and with an expanded knowledge of numbers and, math. Well, in this case, more like number theory. So, I want to just say, I just want to put this a disclaimer, right? I'm not trying to claim that this is my conjecture because it's named the iReapism conjecture. I simply don't know that it exists anywhere else. It probably does. Now, I'll say this. It probably has been conjectured with a 99% chance, right? This probably has been conjectured minimally in some giant discovery in a paper, right? So I'm not trying to humble myself into saying, like, this will be my own ideas. I want to conjecture my own ideas, and I'm the only one who thought this. I don't care about that. I do not care about that at all. I'm only interested in what this idea takes me, because I thought about the idea at one point, and I want to continue thinking about it regardless of if I'm the first or not, because for me, it's just to find the answers that I'm interested in. It's not about if I'm the first one to conjecture the idea. I would like to be, obviously, that'd be nice, but I'm not. That's not going to be the main focus of this conjecture. So if it isn't out there, hopefully I can conjecture it and someone out there can prove it eventually. But before I conjecture, I need to ask for more make more implications for its usefulness. So, in order to begin, we have to establish some of the variables in this form. Now, don't be scared about anything I'm going to show you. It looks scary, but it's very, very simple. Extremely simple, actually. A kid could follow this procedure. So let's just unravel it. Hopefully I can explain it good. So we have four variables. B is the base integer number, a whole number, in the form b to the s, b to the power of s. S is just the exponent in that form, so b to s. S is that exponent. N is the number of digits. Sorry about that. N is the number of digits when you evaluate b to the s. So we'll see an example later. And then R, capital R, is the ratio of s over n. So the exponent over the number of digits that form entails b to s. Now let's just jump straight into it, and we're going to ask a few questions, okay? So b is the base number, the whole, 2 in the form b to s. So this is the form b to s. Okay, let's just see that really quick. Something is happening here. Oh. Well, it's gone. That's weird. Alright guys, I'm back. So to show some examples, we're going to do 2 to the first. And b here is 2. So we're not going to change b. Okay? We're just going to keep it. And we're going to iterate s. Okay, so s is the exponent. So we're just going to take note of some of the variables and what those values hold. So these are our four variables, and we're going to basically find out what they equal. And so we're really interested in s and n because we know b isn't changing, right? B is going to remain 2 until we find another equation. So 2, we don't need to keep writing it. Now let's find out what s equals, n equals, and r equals. So we know that s equals the exponent in this form, and that's 1. And n is the number of digits when you evaluate this guy. Okay, so s equals, well, 2 to the first, and that's equal to 1 digit. Okay, that's equal to 2. 2 to the first is 2. That's 1 digit, so n equals 1. So r is the ratio, s over n. So r equals 1. Okay, so 2 squared, s equals 2, n equals 1 still, because 2 squared is 4. That's still 1 digit. So that's all we care about, the number of digits, not what it equals, guys. And so r equals 2. because 2 over 1 is 2. 2 cubed is s equals 3. Sorry about that. Sorry if it's a little, messy. N equals 1 still, because 2 cubed is 8. That's still 1 digit. So r equals 3. Now, naively, at this point, if you made this observation, that's really good. That's showing that you're trying to find a pattern. And that's all math is, really, finding patterns, right? So, we're trying to find a pattern here. What is the pattern? Well, you can see that r equals s in these 3 cases. Now, this is not going to be the case when we keep iterating. Now, watch 2 to the 4th. S equals 4, but 2 to the 4th is 16. N equals 2. N has finally changed, and now r equals 2. Alright, that's horrible too, but r equals 2. Okay? And we'll just do one more example. 2 to the 5th. Let's do that. S equals 5. And 2 to the 5th is 32. So, that's still 2. N equals 2. And then 5 over 2 is 2.5. So r equals 2.5. I just wrote it differently. Okay, so now that we know this, let's see in a program that I've written how this works. So we're going to iterate s 1,000 times in the base 2. And we're going to find that they equal, basically. R equals 1. So we can see exponent 2 to the 1st, that's s. Number of digits, that's n. So 1, where this equals sign, think about division. So 1 over 1 is 1. And that's what's going to be spit out for r, which is ratio. And then 1, 2. See, we got 2 here. 3. 2 to the 3rd, 3. 2 to the 4th, we got 2. That's right here. 2.5 for 2 to the 5th, right here. And let's just look down. Okay, we don't have to do it by hand anymore. We have this program to do it. And it looks like it's converging. So before we continue, we're asking 2 questions. All right. For what b, when you iterate s, what does r equal? Another way to put it is, does r converge or diverge when s approaches infinity? Okay, so s approaching infinity, we're talking about, we did 5 examples of s. S has to equal infinity now to find out the answer to this, right? Well, let's take a look. Now, we know that this program is showing us some decent accuracy of the ratio. Now, what it's understood, now there's a somewhat proof for this, a potential proof for this, but I don't have it in front of me, but just accept that that proof works potentially and we can go further. Remember, I'm not conjecturing this to the public yet. I'm still working on it. This is a progress video of what I have so far. So, I'm basically saying that the reciprocal of log base 10 of 2, the base, is, whatever that equals, is what r is converging towards. Okay, so let's just take a look at that on this text. As s approaches infinity, r equals exactly, when s is infinity actually, r equals the reciprocal of log of that base. So the base here is 2. We saw that. And that's really interesting, because what we're showing is that we're making a correlation between an exponent of whatever base that is, an exponent, versus the number of digits that entails. And we're finding a convergent number. This number is converging towards a number, and it's not approaching infinity. R is not approaching infinity, so it's interesting, guys, to us. So we're going to go further. Now this works. Any b that's an integer, this was really important from before. B has to be an integer, so any whole number. But there's finite exceptions, which isn't bad. These are kind of the singularities. It's not one singularity, it's 3, I guess. But these are the 3 poles, I guess, to this equation, this function. -1, 0, and 1. They don't work. Watch this. We're going to have to plug in 0. And we're going to get r equals s for any s. Okay, that's just what we're going to get. So clearly it does not work. And the reciprocal of this log equals 0. It says here. So this might actually equal 0. R equals 0 maybe at infinity. Which, you know, it probably is. Maybe it's not an exception. But it seems like an exception. 1 also is an exception because it's doing the same thing. Now, but it's different. The reciprocal of log base 10 of 1 is infinity. Well, it is approaching infinity. But it's not necessarily working. Upon investigating this further, actually, this is much more complicated than it seems. We're receiving infinity as a result of semantic errors within the function itself. It could be infinity, but I'm not entirely sure it is. But these are the 3 exceptions, at least I am sure of. There's not any more than this. And so we can try b for any value. And watch this. B to 10. Well, we know reciprocal of log base 10 of 10 is 1. And watch as it approaches 1. You see that? It's getting really close, guys. Really close. Look, this seems to be an infinite nesting of 3 9s and then 3 zeros, 3 9s, 3 zeros, 3 9s. That's what it seems like. But it's getting really close. Remember, s has to equal infinity. So 10 to the infinity equals x digits, infinity possibly. Well, it will be infinity. So infinity over infinity is 1. This works perfectly. And, well, we get 12. We do 12. We get 0.92. Well, it's going to 0.92. We enter that number. It's going to take a little bit longer. But we get 0.156, 0.156, 9, even 9 we get. Really interesting. So we're approaching. Now, remember, s has to approach infinity for this to really get arbitrarily close to the reciprocal of the base. Now, we want to go further. And this is where I stop my conjecture, really. I want to prove b to be any real number. So we've shown that with those 3 exceptions, with the 3 exceptions of -1, 0, and 1, that b holds for any integer value. This works, okay? Now, b can be any real number. Well, what does that mean? Well, 2.5 is a real number. It's not found in the integers. It's between 2 and 3. And, well, we can do the same thing. However, my program does not like it. Does not like it. So I have debugging for decimals, and it just doesn't work. So as you can see, 1 over 1 should equal 1, but I'm getting a ratio of 3, 0.3 reoccurring. So I have a huge logistical error and somewhat of a semantic error in the code. So, yeah, huge logistical error, it seems. So, yeah, that's we're gonna leave it at that, I guess. So this program will eventually crash. Let's just wait till it does that, and we'll go further. We'll try to go further. It's gonna crash here. There you go. Well, it just stops. But basically, that's what I'm trying to prove. I want to prove that b can be any real number. And when my program kind of works, maybe we'll get an idea that it does actually hold. B can be any real number. In fact, we can go as crazy as pi. Write pi. Put pi to the first. To pi to the second. Oop, that's a horrible pi. Pi squared. Here, let's write it over here. It's much... Or let's write it here. It's way better. Pi cubed, pi to a fourth, and figure out what r equals for any of these values. So it's going to be quite the computation to find that. Quite the code to actually get this to work. But clearly I can't put pi into this, because pi is irrational and it never ends. So I can never truly put pi into this and work it out. But we can approximate it and get other values of b. So you have to prove. It's quite the lengthy proof. But after that, once I do that, go to complex numbers. So a number with two parts. That's what a complex number is. And briefly, I will show you how complex numbers look like, potentially if you have no idea. So here's a real number line. So we have 0 here, 1, 2, and everything in between. Here's pi somewhere over here, right? And then the complex numbers is just another axis. So here's what is this? 2 plus 2i, maybe? That could be. Probably not drawn to scale, obviously. Or, yeah, we have a 2-part. And then I want to go further. 3 parts, 4-part. Numbers, so quaternions are 4 parts, or 3 parts, I believe. And go past that, keep going. But we're going to probably run into a problem there. But that's basically what I'm doing. I'm trying to connect it to other branches of mathematics. Obviously, connecting it to the complex numbers would be quite the step. That's going to be extremely hard to do. But yeah, this would be more accurate. There you go. Yeah, guys, so I hope you enjoyed. It's very not neat. So I apologize about that. But yeah, I hope you understand something about this and maybe the potential it holds. So we went from one solution of 2 to infinite solutions except those 3. So that's basically as far as I went. I still haven't went any further. I haven't gone further, but I want to. So this is kind of a recap of all this. Thanks for watching.